This is video 2 for the waves unit. Let's begin by talking about the Doppler effect. So the observed frequency, remember frequency is how many oscillations there are per second, of a wave depends on the relative motion of the source and the observer. And for the AP exam, this will be qualitative only. We're not going to do any math with this. Okay, so first off, let me show you something called a wave front diagram. In the wave front diagram, these lines represent the compressions, and the space between the lines represents the rarefaction. So we can use these for sound. I can also represent the compression with the peak or the crest of a wave, and then the rarefaction as a trough. So I can represent a longitudinal wave as a transverse wave or a sine curve if I want. So if I have something making sound, and let's say it's stationary, the sound waves will travel out uniformly in all directions. But if the thing starts moving, it's going to compress together the wave fronts in front of it and stretch out the ones behind it. Now the speed of sound stays constant. So when I take a look at my math, what happens is, in order for the speed to stay constant, if the wavelength gets shorter, the frequency must get higher in response. The way we observe frequency is through pitch. So think about a very high note or high pitch and a very low pitch. So what we would perceive then is the pitch getting higher as the object approaches us, and once it passes us, the pitch getting lower. There is a mathematical formula for this. I'm going to modify it just a little bit. To pluses and minuses. So on the top, using this formula, what this means, F is the frequency of the source, F prime is the new perceived frequency, V is the speed of the wave, and V naught is the speed of the observer, and then Vs is the speed of the source. And basically on the top here, you would use a plus if the source is approaching you, or I'm sorry, when you approach the source. You'd use a minus when you go away from, so when you move away from the source. So as you approach, so let's say there's a source of sound that is not moving, like a siren, and you run towards it, you would perceive the frequency to be higher than it actually is. If you run away from the source, you would perceive the frequency to be lower than what it actually is. And that's if the source is stationary. If you just stop moving, then you would hear the true frequency. And then on the bottom here, you'd use a plus when the source is approaching you, or when you're getting closer to the source, and then a minus when you approach. And again, we're not going to use this math, but I felt it important to throw in here. So there could be a situation when you and the source of sound are approaching each other, or when you and the source of sound are moving away, or if you're moving at one speed and the source is moving at a faster speed toward you. There's all kinds of different configurations with this. We can also apply this to light or an electromagnetic wave. You have probably heard the acronym ROY-G-BIV. You know, the 7 colors of the rainbow. This also gives us the order of light in terms of increasing frequency. So let's say I have a source that happens to be light. See, the Doppler effect works for all waves, not just sound. So let's say I have a star, and that star is moving toward me. Because of the Doppler effect, the frequency would be increased. So I would see an overall shift toward the blue end of the spectrum of that star. So if it's like a white star approaching me, it would start to kind of look a little bluish, even though it's white. And if the star is moving away from me, I would see kind of a reddish color to that star. So by doing this, we can tell whether or not stars are moving toward us or away from us. And looking at the frequency of light, we can also kind of get an idea for how fast it's moving towards us or away from us. Okay, now the next topic is going to be superposition. So when we have 2 or more wave pulses that are heading toward each other, they can interact in such a way to produce an amplitude or vibrations in the resultant wave. So when 2 pulses cross, they travel through each other. They do not bounce off each other. This is another property of waves. They can pass through each other. And when their pulses overlap, the resultant displacement can be determined by adding the amplitudes of the original 2 pulses. We call this superposition. So first off, we have constructive interference, where we have A and B approaching each other, and then we get A plus B. Notice how the amplitude is now twice as high, and then notice how B and A go about their separate ways after interacting. And we can get all kinds of weird things. So let's say a pulse, it doesn't have to be a circle. So let's say we have these 2. This is A and this is B. Well, when these 2 interact, it might look something like this. When those 2 interact with each other. And there's all kinds of other geometry we can take a look at. So again, this is constructive interference. Destructive interference, one of the waves has a negative amplitude. Now, this is an example of complete destructive interference. We can't have partial destructive interference, where, let's say, A is positive 2 and B is negative 1. Well, positive 2 minus 1 equals positive 1. So we would still see an amplitude, but it would be a diminished amplitude. So, these are just some ways in which waves can interact with each other. Now let's think about sending wave pulses on a string, but the string changes. Well, first off, let's talk about how to calculate the speed of a wave on a string. So the way we calculate the speed of a wave on a string is by taking the tension force, so how taut is the string, dividing it by some value called mu, and then taking the square root. So this calculates the speed of a wave on a string. Mu is called the linear density, and it'll equal the mass of the string divided by the length of the string. So by using these 3 numbers, how much force is there, what's the tension force in the string, the mass of the string, and the length of the string, we can then calculate how fast a wave on that string would go. And we can also apply this then to our math wavelength times frequency. And notice then, if I plug in some values here, notice then if I were to keep everything constant but adjust the tension, I could, if the tension becomes higher, the frequency can become higher. Or if the tension becomes lower, the frequency becomes lower. That's how guitarists tune their strings. They're adjusting the tension by adjusting a knob, and that changes the frequency. If I use different strings, if the tension stays the same, everything stays the same, and I use a more massive string, well, as M gets bigger, the frequency gets lower. Hopefully you guys can see that. If I use longer strings, well, as L becomes longer, the frequency can become higher or lower. It kind of depends on a few other things, but hopefully you get the idea. So let's say I send a wave pulse down a string, and the string is attached to something so that it cannot move up and down. Well, this wave pulse will be reflected, but it will be reflected on the inverse. It'll flip upside down. If I send a wave pulse along a string and then there's a movable boundary, the wave will be reflected, but this time it will stay at the same amplitude that you send it. If I send a wave pulse down a thin string and it encounters a thick string, it'll be reflected. It's kind of like hitting a fixed boundary. It's going to be reflected, but some of the energy transfers into the thick string. Likewise, if I send a wave down a thick string and it encounters a thin string, it'll be reflected, but also it'll send some energy down the thin string as well. Except that one it didn't get inverted. It's like hitting a loose boundary. When we have two or more traveling waves, we can see that they can interact in such a way to produce amplitude vibrations and a resultant wave. So in other words, two waves can interact with each other, and we can create things, some areas of constructive and destructive interference. So far we talked about wave pulses, but we can also talk about periodic waves. So let's take a look at these two things that are oscillating right here. So I got one oscillating here and I got a second one oscillating. If these two oscillate at the same frequency with the same amplitude, we will get regions of constructive and destructive interference. So I'll use red to highlight the destructive interference. So notice that along these paths right here, the waves cancel each other out. And I get places where they reinforce each other to have constructive interference. So I get constructive and destructive interference. And again, this happens when the two waves have the same frequency. So that's very important. We can do this with light. We can shine light through two openings and we'll see an interference pattern. We see this in concert halls. People who design concert halls have to be very, very careful about placement of the speakers because we can have regions of destructive interference. Now, this picture might kind of look like a concert hall, and there's a reason for that. When they do design concert halls, they try to be careful and put the walkways where there's destructive interference. And you may have noticed this if you're at a concert, when you go to leave to get a snack or something, it kind of sounds a little bit quieter. That's because when you step out into a walk area, you're going into a destructive interference zone, and the sound gets quieter. What happens, though, if the two waves have different frequencies? Well, then we'll get something called beats. So what happens is that some of the waves will line up for constructive interference, and then it'll kind of line up for destructive interference, and we'll get a beat pattern. Now, the way we calculate that beat pattern is by taking the first frequency minus the second frequency. And we just look at positive values. So if one frequency has or one sound has a frequency of 440 hertz, and another one has a frequency of 430 hertz, we would have a beat pattern of 10 hertz. And you would hear like a wah, 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 wah kind of sound to it. Musicians use this to help tune. So, as I'm tuning my saxophone, I'm listening to another sound, another source of sound as a reference, and if I hear this wah, 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 wah sound, then I know I'm out of tune. And then I adjust my frequency by changing things on my saxophone to get myself in tune. So this would be like again, this is kind of like an interference pattern, but it's kind of unique. I'll do some demonstrations in class to let you observe what this is all about. All right, that's going to conclude video 2.